It's all thanks to Doppler radar signal processing. In this video, we'll explore how Doppler radars use the Doppler effect, the change in frequency of waves due to motion, to detect speed, direction, and movement. From military applications to autonomous vehicles, Doppler radar is a game changer in modern signal processing technology.
In this video, we are going to simulate a continuous wave Doppler radar system using Python. First, we need to set up our physics. We start with a carrier frequency, or f_c, of 1000 Hz. This is the tone our radar transmits. We also simulate a moving target. We are manually setting a Doppler shift fd of 20 Hz. In a real scenario, this is the unknown variable we are trying to find. But here, we define it to verify our math later. We set our sampling frequency to 5000 Hz. According to the Nyquist theorem, this must be high enough to capture our signals without aliasing. Next, we generate the waveforms. Tx is our transmitted reference signal, a perfect Cassini wave. The x is our echo. Notice its frequency is the carrier plus the Doppler shift. But real radar isn't perfect. We add random Gaussian noise to this signal. This mimics atmospheric interference and thermal noise, burying our target data. Now for the signal processing. Step 1 is mixing. We multiply the noisy echo by the transmitted signal. Mathematically, this creates two new frequencies, a high-frequency component we don't need, and a low-frequency component, which is our 20 Hz Doppler shift. To isolate that 20 Hz shift, we use Butterworth low-pass filter. We set cutoff at 100 Hz. This filter acts like a gate. It blocks the high-frequency noise and carrier harmonics, but lets low-frequency speed data pass through. Finally, we need to know exactly what frequency passed through the filter. We use the fast Fourier Transform. FFT takes our time domain signal and breaks it down into frequency bins. We then use argmax to find the exact index where energy is highest. That peak is our measured Doppler shift. The output shows the following. Top graph: this is what the radar antenna actually sees. It's just noise, you cannot see the target. Middle graph: this is after mixing and the Butterworth filter. We've successfully recovered the beat signal. It's a clean sine wave. Bottom graph: the FFT spectrum. It ignores the timeline and looks at frequency. We see a massive spike, exactly at 20.00 Hz. The math worked. When I close the plot, the script proceeds to the final calculation. It takes that measured 20 Hz peak, applies the speed of light and our carrier frequency formula.